Hello guys, welcome to the 8th session under the Scikit Learn series. Today we are going to discover the kmeans algorithm in Scikit Learn. But before we get started with that, make sure you guys hit that subscribe button and bell icon so that you'll never miss any update from Intellipaat YouTube channel. That being said, let me take you guys through the agenda for this session. We'll begin this session by understanding what clustering is. Then we'll talk about the k-means algorithm, different measurement metrics involved in it, and how it forms the clusters with its algorithmic process. And finally, we'll delve into the hands-on demo where we'll develop the k-means model with the help of scikit-learn library. I hope the agenda part is clear to all of you guys out there. So, without further ado, let's get started with the first topic of this session, that is, what is clustering? Guys, clustering is one of the most common exploratory data analysis techniques used to get an intuition about the structure of data. It can be defined as the task of identifying subgroups in the data such that data points in the same subgroup are very similar while data points in different clusters or subgroups are very different. In other words, we strive to discover homogeneous subgroups within the data so that data points in each subgroup or cluster are as comparable as possible based on similarity measure like Euclidean based distance or correlation based distance. Guys, the choice of similarity metric to utilize depends on the type of problem you are solving or your dataset. Unlike supervised learning, clustering is considered as unsupervised learning method since we don't have the ground truth to compare the output of the clustering algorithm to the true labels to evaluate its performance. We only want to try to investigate the structure of the data by grouping the data points into distinct subgroups. Now that we have built basic understanding for clustering, let's talk about what is k-means clustering. Guys, k-means clustering is a technique for unsupervised learning. Unlike supervised learning, there is no label data for this grouping. K-means divides things into clusters that share similarities and are distinct to the objects in another cluster. The letter K represents the number of clusters that you are wishing to formulate. You must inform the system how many clusters you require. Alright, that means K value will be provided by the programmer. Now, for a better understanding of K means, let's take an example where we have been given the height and weight of few personnel. And based on these details, we are supposed to group the data into two clusters, namely OBs and non-OBs. Basically, we are supposed to find out the body type of a particular person when the weight and height is given. Here we have our data set plotted on x and y coordinates. The information on y axis is about height of personnel and on x axis about the weight of them. If we plot the data, this is how it looks like, alright. Now by looking into this data, we need to formulate clusters. The value of k for this sample will be 2. I mean, it will be either obese cluster or non-obese cluster. The first step in k-means clustering is the allocation of two centroids randomly. As k is equal to 2, we'll have two centroids in this particular sample. Then the 2 points will be assigned as centroids. Note that these points can be anywhere as they are random points. They are called centroids, but initially they are not the central point of a given data clusters. Alright. The distance between each of the randomly allocated centroids and the data points is then calculated. Basically, the distance between both centroids and all the data points determines to which centroid the data points will be assigned to. Then we'll move on to the next step. Here, we'll determine the actual centroid for the clusters. The originally randomly allocated centroids will be repositioned to the actual centroid of cluster. This process of calculating the distance and repositioning the centroid continues until we obtain our final cluster. Then the centroid repositioning stops. In this graph, the centroid doesn't need any more repositioning, and it means the algorithm has converged and we have two clusters with two different centroids. Now, how exactly are we going to compute the distance between centroid and other points? Well, for that purpose, we have four different methods. First one is Euclidean distance measure. If we have a point P and Q in a plane, then the Euclidean distance is an ordinary straight line joining these points. It is the distance between the 2 points in Euclidean space, or what we call planes in simple mathematical terms. The formula to calculate Euclidean distance is pretty simple. All you have to do is take the difference between the coordinates, square them and place them under the square root. Alright. Next we have is the Manhattan distance measure. The Manhattan distance is the simple sum of horizontal and vertical components of the distance between 2 points measured along axis at right angles. Note that we are talking the absolute values so that the negative values don't come into play here. That is why we have incorporated modulus sign in formula as well. The formula for Manhattan distance will be mod of xa minus xb plus mod of ya minus yb. Alright. Third up is squared Euclidean distance measure. As its name suggests, it is nothing but the square of Euclidean distance. So the formula for squared Euclidean distance will just not contain the square root computation. Alright. So it will be q1 minus p1 square plus q2 minus p2 whole bracket square. Alright. Now let's talk about the final metrics we have on our list, that is cosine measurement. Mathematically, cosine measurement measures the cosine of the angle between two vectors projected in a multi-dimensional space. So, if we consider 2 points A and B as the vectors originating from the origin, then we'll compute the cosine of angle between them. If the distance between two vectors is high, the similarity will be less, and if the distance is less, the similarity will be high. The formula for this measure is given on your screens, guys. Now moving forward, let me tell you how the k-means algorithm literally works. The k-means algorithm's purpose is to detect clusters in the provided input data, and here are the steps involved in it. The first step is finding k value, then we have measuring distance, then grouping, then repositioning centroids, and finally the convergence. Basically, the algorithmic procedure begins with finding the optimal value of k. Now, there are a few options for doing so. We can even use the hit and trial method for specifying the value of k. And as we progress, we keep changing the value until we get the best clusters. Another way is to use elbow method to calculate k. Even in this method, you start with some random value of k and then you try to compute the within sum of squared error. What this matrix means is that for each cluster, you try to compute the distance of individual data points from the centroid. You square it and then you sum it up. Furthermore, you combine these SSEs to compute the value for WSS. Now the next thing I'll do is I'll compute these WSS values when k is equal to 3, 4 and 5 and so on. And after all these computations, I'll plot a graph for WSS versus k. From this graph, you can intuitively see that the values of WSS decreases with the increase in value of k. I mean, it's pretty obvious. After many iterations, you can consider each data sample in your dataset as an individual cluster where your value of WSS almost becomes 0, or rather becomes 0. But we're actually after the most optimal value of k, if you remember. So the general guideline to follow is that you guys find an elbow in your graph. So in this graph, if you observe this point, it seems like it is an elbow. So ideally, this number should be the best optimum value for k. Now once we know the optimum value for the number of centroids, we assign the random points in the plane called centroids to these clusters. In the second step, the distance of each data point from the centroid is measured, and each data point is assigned to the particular centroid which is closest to it. Then the next step begins, known as grouping. Here based on the distance matrix, each data point will be assigned to the centroid. This initial gathering of data points is known as initial grouping. Now the next stage will be bringing centroids to the optimum position. Now we'll move the old positions of our centroids towards the center of whole data cluster, and we'll calculate these positions by repositioning centroids and calculating the distance between data points and centroids. Now once the centroid reaches its mean position, the iteration will stop and the model will be said to be converged. This is the exact workflow of kmeans algorithm. Now moving forward, we'll dive into the hands-on demo where we will develop kmeans algorithm on Scikit Learn dataset known as Wine dataset. Alright guys, let us begin this kmeans implementation by importing few important libraries. First of all, I'll import pandas library. Then I'll import numpy. Next, we are also going to load the toy dataset framework from Scikit Learn, and the syntax to do that is from Scikit Learn import datasets. And the dataset that we are going to use for this particular session is going to be a wine dataset. So let me load that to our notebook with the help of load_wine function as well. So I'll set data is equal to datasets dot load underscore wine, and I'll run this block. Now our data has been loaded into this data variable. So let me split it into x and y. So x will store the feature data and y will store the target label or column. Alright, so x is equal to data dot data and y will be equal to data dot target. Now guys, we previously discussed that the label data is not provided in case of clustering problems, since it is an unsupervised learning algorithm. It is merely exploratory technique of formulating the labels via learning the similarity in features. So we are not going to use this target column throughout this notebook. Although since we do have it for this dataset, we can measure the accuracy of our KNN model predictions by comparing them with the target column. Alright, so we'll use it at the end. But before that, now using these components x and y, let me show you how our dataset looks like in a tabular format. For that purpose, we are going to require a data frame. So let me create the data frame. df is equal to pd dot data frame, and inside it I'll store the feature data and I'll set column names as data dot feature underscore names. Then I'll create a new column for this data frame and I'll name it as wine class, and inside it I'll store the target. Now let me print this data frame. Here you can visualize how your data set looks. There are 14 columns in our data set and around 178 rows. So the values that we have, the features that we have are alcohol, malic acid, ash, alkalinity, magnesium, total phenols and many more. Now moving ahead, let us get the more information about our dataset. So the first thing we check in pre-processing is missing values. So let me check if we do have null values or not. So df dot is null dot sum. From here you can see that we have no missing values for imputation purpose here. Now we'll use describe function to know more about mathematical statistics about our data such as mean and standard deviation. So the command is df.describe, and once I run it, I'll get this tabular information about my dataset. Basically, we have mean and statistics present inside this table. So mean will tell us the average value particular feature takes in, and standard deviation will tell us how the data is distributed with respect to the mean value. Now from this particular table you can find out that in terms of whole data set, the mean value is quite varying nature. What this suggests us is that our data set requires proper scaling, and the method of bringing data to one scale is standardization. We'll use standard scalar method here so that mean for all our data feature will chop down to 0. So let me take a new block here and create the standard scaling procedure. So first I'll import the standard scalar from sklearn dot preprocessing. Then I'll invoke the object of this standard scalar and I'll fit our data to it. And I'll run this block. Okay, there is one spelling mistake over here. Fit underscore transform. This should be fine now. Now that our data is ready and processed, we'll go ahead and create the kmeans model. But to do that, let me import the instance of kmeans from the sklearn.cluster framework. So I'll take a new block and I'll import the kmeans from sklearn.clusters framework. And as we discussed earlier, the kmeans model requires us to tune the k value. I mean, we also mentioned that we could use hit and trial or elbow method to determine this k value. For this exploration, we'll be using the elbow technique. Now to visualize this elbow, we'll have to calculate SSEs and merge them together to figure out within squared sum error or WSS value. Guys, we'll be calculating these values by changing k is equal to 11 to k is equal to 11. Because for this sample, I don't think we need to loop further than that. So let me create the for loop ranging between 1 to 11 first. So I'll create the for loop for I in range 1 to 11. Apply the k-means on our data set. I'll send in the number of clusters as I, and it will be set to k-means. So if I set init is equal to k-means, then the empirical formulation will be used to set the initial random values, alright, and I'll also set random state to 0, alright. It should be n underscore clusters, and this c should be small as well, and I'll store these values inside a list. So first of all, I'll need to create the list, and WSS values will be stored inside this WSS list, and the function that returns the WSS values is inertia underscore. Now let me run this block. Okay. Oh, we are missing one comma over here. So let me rerun this block. Yeah, this should be k-means plus plus or random, and this should be inertia. Now the next step will be plotting the graph. So for that purpose, I'll do f3 comma axis is equal to plt dot subplots, and I'll set fixed size equal to 8 by 6, and we'll use plt dot plot. Range will be between 1 to 11, which will be plotted on the x-axis, and WSS will be plotted on y-axis. but we'll also need to import the matplotlib library as well. So import matplotlib.pyplot as plt, and then we'll also set the title, x label and y label. Now the title will be, let's say, the elbow method. Label will be, x label will be number of clusters and y will be WSS. Now we'll print the graph. Let me run this block. From this graph given here, you can say that the elbow is getting formed at k value 3. Alright. So we are going to provide this value to our model while training it on our data. Alright. So now let us create the new coding block, and we'll set number of cluster n is equal to 3, and we'll create the new kmeans model. We are again going to set init is equal to kmeans plus plus the number of clusters will be 3 this time, and we'll fit our data with this model. Then label, that is the outputs or the clusters that our model has formed, will be k underscore means dot labels underscore. So basically labels underscore method will return the predictions made by the model, and finally we'll print these labels. K should be small, k means dot labels. Now let me run this block, and here you can see that we are getting the output values. Now let me import the accuracy score module to evaluate the accuracy of our k-means predictions. So from sklearn dot metrics import accuracy underscore score, and the accuracy score will be provided on labels and y. And from here you can see that we are getting very less accuracy. At the beginning we saw that accuracy was very less. It was almost nullified. So to improve the accuracy, what we did is we added some seed to our dataset, as well as we increased the number of iterations, that is to 360, and we rerun this block. After that, the accuracy that we are getting is almost 96%. So guys, what we did is we added few hyperparameters to our k-means model, and it actually helped us to improve the accuracy of our model. Alright, now I hope this part is clear to all of you guys out there. That's all we have for this k-means implementation process. I thank you all for being here till the end of this video. I wish this session was informative and exciting. If you have liked this video, a thumbs up would be much appreciated. Also, hit the subscribe button so that you never miss any update from Intellipaat YouTube channel.
If you want to make a career in data science, then Intellipaat has IIT Madras Advanced Data Science and AI Certification Program. This course is of very high quality and cost effective, as it is taught by IIT professors and industry experts.